De cara a obrir la sessió pública, us volia presentar al tribunal, que crec que els coneixeu, el professor Macanàs, desagregat de Departament d'Enginyeria Química de la UPC, i el Sergio Ponsà, que és professor titular de la Universitat de Vic, i jo mateix, que soc professor d'aquest departament. Antes move to the English, or is okay in Spanish, Amman? English? Está bien, está bien. ¿Está bien en Spanish? Okay. Only few. Lo primero es comentaros a todos el sistema de puntuación para la tesis. La tesis, ahora abrimos la sesión, ahora es la presentación en un tiempo máximo de 1 hora. Después pasaremos a hacer las preguntas, haremos la deliberación y se te otorgará una puntuación. Y después hay una segunda fase, que es el cum laude, que es si obtienes la calificación de excelente en la evaluación de la tesis, entonces tienes posibilidad de acceder al cum laude, que es un sistema, que el procedimiento es un procedimiento secreto, que se abren los sobres en la escuela de doctorado, y siendo viernes, el lunes o el martes, me parece que son 48 horas, pero no sé si son hábiles o no, te comunicarán si tienes el cum laude o no tienes el cum laude. ¿Entendido? Bueno, sí. Perfecto. Pues then you have 1 hour to explain the principal points of your research during these 4 years.
Thank you very much for this introduction. Today I would like to present my work during my PhD, entitled Environmental Application of Engineered Nanomaterials, Sense and Characterization, supervised by Professor Xavier Font and Dr. Amanda Alonso. I'd like to thank the Egyptian Ministry of Higher Education and Scientific Research for the PhD grant. Outline of this presentation will be a brief introduction, research objectives, general methods and materials, results and discussion, which will be divided into main parts for water remediation and gases treatment, and then general conclusion, finally, for future work. Brief introduction: any undesirable change for any component, such as chemically, biologically, into the environment, which can cause harmful effect to the environment, can be called environmental pollution. 3 main types of the environmental pollution, which could be water pollution, air pollution, and soil pollution. And here in this study, we're going to focus for water pollution and air pollution. First of all, for water pollution, due to the tremendous increase of population, industrialization, and the increase of demand of fresh water for several fields such as agriculture and industrial and domestic, so water contamination become a serious problem overall the world. Sources of the water pollution could be municipal wastewater, industrial wastewater, and agricultural wastewater. Several contaminants have been registered as a contaminants of emerging to be concerned, such as inorganic anions, for example, fluoride, nutrients as a phosphate and nitrates, heavy metal, for example, cadmium, nickel, lead, and chromium, persistent organic pollutants, as a organochlorine pesticide, organophosphate pesticide, and the carbamates, and among others as a pharmaceutical and microbial. Several techniques have been used in the literature for water remediation, such as chemical prestation, electrocoagulation, biological treatment, and adsorption method. For the first one is a chemical prestation, which based on the use of prestating agent of metal divalent or trivalent metal to form a prestate. However, the drawback of this method could be from the high production of sludge and the complexity of the process. And secondly, for the second method, which is electrocoagulation, which means the application of electric current for an anode of metal ion of iron or aluminum. However, the drawback of this method is based on the high cost of energy and anode passivation. Third methodology is the biological treatment, which could be anaerobic or aerobic process. And recently, increased attention by using the microalgae for nutrient elimination. But The drawback of this method can come from the harvesting of this microalgae from water. The another method which has been used for remediation is the absorption method. This method is based on a phase transfer to remove any substance from fluid phases, such as air or gases. And this method is the most promising method for water remediation due to the low cost and the easy operation. Absorption method can be an adsorbate which contains a contaminant, adsorbate in a medium, and then by contacting with an adsorbent and leaving until achieving the absorption equilibrium, then we can separate the adsorbent with adsorbate and the treated medium. Then, after applying a regeneration process, we can separate the adsorbent from adsorbate, and optimization of the reusability and regeneration, then we can use our adsorbent for another cycle for remediation. 5 main possible mechanisms of adsorption, which could be as inner sphere complex. For example, ligand exchange, hydrogen bonding, which is the most suitable for fluoride, phosphate, and the heavy metal. And another one is outer sphere complex, for example, as ion exchange, van der Waals, and which is the most suitable for fluoride and phosphate removal, and surface prestation, diffusion, modification of the adsorbent surface. The second type of pollution that we're going to focus in this study is air pollution. 2 main sources for the air pollution, which can come from the increase of the greenhouse gases, which means the main source of these greenhouse gases from carbon dioxide as a fossil fuel combustion, or methane from natural gas system, or hydrofluorocarbon, perfluorocarbon, sulfur hexafluoride, and nitrous oxide. The second source of air pollution can come from carbon monoxide. The main source of carbon monoxide can be from cigarette smoke, vehicle exhaust, fire of houses, and burning of woods. How we can remediate air and gases? By using a novel technology, which is named a nanotechnology. What does it mean, nanotechnology and nanomaterial? Nanomaterial, in general, any material with at least 1 dimension less than 100 nanometers. And nowadays, since 2010, as we can see from this figure about the application of the nanomaterials in several fields, linear exponential, which means this new technology could be applied in several applications. Among the several applications of nanotechnology, such as household, energy, information technology, medicine, industry, and finally as an environmental, which is the most important now for remediation, such as water and gases. What could be the classification of nanomaterials? Could be in 4 main types, as a carbonaceous, fluorine, carbon nanotubes, and graphene. The second one, metal-based, as a silver or metal oxide, cerium oxide, titanium oxide, or magnetite as iron oxide, and also for metal-based as a quantum dot. The third part as a dendrimers, such as the polymer with the branched units. And lastly, with a composite, which can be composed as a mixed oxide, core shell, and supported nanoparticles. Here in our study, we're going to focus on the graphene carbonaceous nanomaterial, metal oxide nanomaterial, and for the nanocomposite as a mixed oxide, core shell, and supported nanoparticles. What does it mean, nanocomposite? It means more than 1 nanomaterial. For the first one, as a mixed oxide, means like 2 phases of nanomaterial in 1 nanomaterial. And the secondly, for the core shell, means we have a 2 nanomaterial, one as a core, coated with the shell of another nanomaterial. Which types of core shell nanomaterial could be classified into a combination of organic and inorganic nanomaterial. And the shapes of this core shell nanomaterial could be as a spherical core and shell, could be a hexagonal core and shell nanomaterial, could be a multiple spore core with a single shell, and a movable core with a hollow shell material. The another type of the classification of the nanocomposite is a supported nanoparticles. This type can be divided into a polymeric nanocomposite, which depends on the use of a cationic or anionic exchange polymer. And another one is a carbonaceous nanomaterial as a graphene oxide nanomaterial. As we can see, this type contain function of hydroxyl and the carboxylic. And the third one is an organic framework by using organic ligand, for example, dibenzene carboxylic acid, and then by encapsulating with a metal or metal oxide to form a metal organic framework, which we can be used later for carbon monoxide oxidation. Here, as we can see, the organic framework, and after encapsulating of metal and metal oxide, then we obtain a metal organic framework. Different adsorbents have been used for water remediation. As example, metal and metal oxide. And these type of nanomaterial could be used due to the low cost and high efficiency. And also for the carbon-based due to the large surface area. However, the problem of these type of nanomaterial can be from the aggregation, can be from the difficulty to separate. And how to overcome this problem? To obtain a nanocomposites. As I mentioned before, that different types of nanocomposites. For air pollution, which adsorbent could be used for the separate or capture of carbon dioxide and methane, different types of adsorbents. As a conventional one, for example, activated carbon and natural zeolite. As a novel adsorbent, as ionic liquid, which based on organic or inorganic anion could be interact with organic bulky material. And the second one as a modified support by doping metal ion into a templated zeolite. And now for nanomaterial which could be used for carbon dioxide and methane capture, as example mesoporous silica, metal and metal oxide, carbonaceous and metal organic framework. Screening of different adsorbent for carbon dioxide and methane capture have been published in the Science of the Total Environment. So from this brief introduction, what could be our research objectives will be divided into three main parts. First one is the sense and the characterization of different types of nanomaterial. The second one is the application for water remediation by first of all make a screening of synthesize different nanomaterials with different pollutants, and then selected the best one for fluoride and phosphate removal, and finally to test the harvesting efficiency of the magnetite-based nanomaterial for microalgae harvesting. The third part will be for gas streams, which could be divided into the catalytic oxidation of carbon monoxide, and second one as application of magnetic polyurethane foam for methane absorption. General methods and material used in this study. First, to characterize our nanomaterial, we have been used different techniques and the function of each one. As example, to determine the metal ion in the nanomaterial, we used two types of inductive coupled plasma with optical emission and the mass spectrometry detector. And the second one to estimate the crystalline structure using the X-ray diffraction pattern. To obtain an information about the size, morphology, and composition using transmission electron microscope, and about the surface of the nanomaterial using the scanning electron microscope. And when we prepare a complex nanomaterial by using a scanning transmission electron microscope. And what about the stability of the nanomaterial in suspension by using zeta potential measurement. When we apply or to remove any contaminant, so the analytical methods used in our study: ionic chromatography to determine phosphate, fluoride, and nitrate, by using biosystem analyzer to determine phosphate, ultraviolet visible spectrophotometer to determine heavy metal as cadmium, and using turbidometer for microalgae determination, and lastly gas chromatography. We use three types of detectors. For example, as atrazine to determine gas chromatography using mass spectrometry detector, and by using flame ionization detector to determine methane, and TCD detector to determine carbon monoxide, which is oxidized to carbon dioxide. The fourth part, which is the result and discussion, as I mentioned before, divided into main parts as a water remediation and gases treatment. For the first part is divided into 5 main parts. The first one is the engineered nanomaterial sense characterization and its potential efficiency on water remediation. Secondly, novel magnetic core shell nanomaterial as adsorbent for water contaminants removal. Third one, the absorption process of fluoride with the magnetic core shell nanomaterial. And fourth one, the phosphate removal and recovery using a magnetic nanocomposite. And lastly, the optimization of the microalgae harvesting using a magnetite-based nanomaterial. So the first one for the engineered nanomaterial, based on the experience of our group and from the literature, we synthesize different nanomaterials. Which nanomaterial? We already synthesized as a metal oxide, for example, magnetite, cerium oxide, titanium oxide, and for carbonaceous one, graphene oxide and reduced graphene oxide, and for the nanocomposite as a magnetite and cerium oxide encapsulated or anchored in reduced graphene oxide, and lastly that supports as a chitosan and the catechol. And what about the contaminants that we already tested for this nanomaterial, such as fluoride, nitrate, phosphate, nickel, cadmium, and atrazine? We compare all of these synthesized nanomaterial with a reference adsorbent, such as activated carbon, which is supplied from Merck, with less than 100 micrometer particle size, and another one, as zeolite, supplied from Sigma-Aldrich, less than 45 micrometer particle size, and a cationic exchange polymer coated with C100 from pyrrolite with ion exchange capacity of 2.3 milliequivalent per gram. Screening of this nanomaterial we did after characterization, for example, of magnetite. As we can see using the transmission electron microscope, we obtain around 13 nanometer of the magnetite. And by using electron diffraction pattern, we obtain a crystalline structure due to the white ring, as we can see, of magnetite, and the confirmation of the elemental composition of magnetite, as we can see, iron and oxygen. Using the EDS spectra, we obtain or we confirm we have a magnetite structure. Screening of this nanomaterial, when we apply for anions removal, as we can see from this figure, which is plot of the absorption capacity under equilibrium versus adsorbent. What we can see, high absorption capacity was obtained using the cerium oxide, followed by titanium oxide and magnetite. And comparing with the reference adsorbent of zeolite, then we confirm that we have high absorption capacity using the metal oxide nanomaterial. For nickel and cadmium removal, we already did like a screening with a magnetite and cerium oxide and magnetite and metal oxide in reduced graphene oxide. And we compare with the cation exchange polymer and activated carbon as a reference adsorbent. And what we could obtain here, high adsorption capacity of nickel and cadmium using the magnetite and the magnetite in reduced graphene oxide, and also for C100, which is a cationic exchange polymer. And thirdly, for the pesticide removal, comparing the magnetite and core in reduced graphene oxide and comparing with the activated carbon as a reference adsorbent, also we obtain high adsorption capacity, but lower than the activated carbon. But in terms of the reusability and regeneration, we can use the magnetite within core and reduced graphene oxide due to the presence of iron with highly magnetic properties. So which summary we can conclude from the first part? By applying different metal oxide nanomaterial for different contaminants, high absorption capacity using magnetite, cerium oxide, and titanium oxide. So we are thinking if we can synthesize a novel material which can contain the 3 metal ion in one adsorbent by forming a bimetal oxide and core shell nanomaterial, which I will be discussed in the second part, in the next part. The next part is a novel core shell nanomaterial for water contaminants removal. Our objective when we synthesize any nanomaterial, we are thinking in 4 parts. First one, how we can synthesize this nanomaterial, and secondly, to estimate the maximum absorption capacity, what could be the method to regenerate this nanomaterial, and lastly, how many cycles we can reuse this material for the remediation. For the core shell nanomaterial, we use the intermatrix method, we use a Crustacean method to synthesize the magnetite as a core shell, as a core, which based on the ion cursor of iron 2 and iron 3, and by addition of aqueous ammonia and mixing under atmosphere, then we obtain the core of magnetite. And to coat this magnetite core with a shell of cerium and titanium, we mix the magnetite with the cerium and titanium salt after sonication of magnetite, then adding of aqueous ammonia and adjusting the pH, then we obtain the core shell nanomaterial in theoretical. But we should confirm if we have a core shell nanomaterial or a mixed oxide. So characterization of this nanomaterial synthesized, we already did a characterization of the bimetal oxide as a cerium titanium, and using transmission electron microscope, we obtain 1 to 2 nanometers of the bimetal oxide and amorphous structure by using electron diffraction pattern. And what could be when we impregnate a magnetite into the bimetal oxide? So we obtain using the transmission electron microscope from 10 to 15 nanometers, and using electron diffraction pattern a crystalline structure. But also from TEM, we didn't have any confirmation of if we have a core shell or a mixed oxide. So we did a confirmation using another technique. After a confirmation which elements that we have in this nanomaterial, using the electron spectra, EDS spectra, as we can see from this figure, we obtain the 3 metal ion of cerium, titanium, and iron. For this complex structure as a magnetic core shell nanomaterial, we used a technique, as I mentioned before, scanning transmission electron microscope, which is based on density-based contrast. What does it mean? We have a core with a shell, and using this technique, the core should be upright and coated with a shell. As we can see, upright here, which correspond to the magnetite, and coated with another, which is theoretical with a cerium and titanium oxide. Confirmation of this by did like a scan ion profile from all of this area. As we can see, a strong peak in the center, which is correspond to the iron, and on both sides we have a cerium and titanium. So now we have a confirmation that we synthesize a core shell nanomaterial. What about the application of these for contaminants removal? We use for this absorption study a batch experiment, which based on adding the core shell nanomaterial into the contaminants, did a shaking and leaving the nanomaterial until achieving the absorption equilibrium for 24 hours. And then we did a magnetic decantation using a permanent magnet. Due to the presence of magnetite, we have highly magnetic properties, as we can see by using the permanent magnet. So we can separate two phases, the aqueous solution and the adsorbent with adsorbate. So this aqueous solution, we can determine the residual to estimate the efficiency of this core shell nanomaterial for contaminants removal. As we can see, by applying our core shell nanomaterial to eliminate phosphate, fluoride, nitrate, and heavy metals, we have around 100% removal for fluoride and phosphate, and for nitrate, 85%. By applying for heavy metal, we have a low removal percent, which is due to the positively charged of this core shell nanomaterial. And comparing with another adsorbent in the literature, so our core shell nanomaterial highly competitive for water remediation. Which conclusions from this part? Magnetic core shell nanomaterial have been synthesized using one-path synthetic method. The magnetic core shell nanomaterial positively charged. The removal efficiency at pH 7 for nitrate would be 85 and ranging from 85 to 100% removal. And this core shell nanomaterial as adsorbent, it's highly competitive and highly magnetic properties due to the presence of magnetite. And this result has been published in RC Advances. From the previously results, we select fluoride to test what could be the parameters for and optimization for the absorption of fluoride using the bimetal oxide and the core shell nanomaterial. And why we choose fluoride first? Because fluoride have dual function as a beneficial and adverse effect. When fluoride ion exists in water below the maximum contaminant level, which is 1.5 milligram per liter, which is a benefit to the human, especially for the bones. And when exceeds this concentration, lead to afluorescence. Then we should eliminate if the fluoride concentration is higher than 1.5. Several adsorbents have been used for fluoride removal, such as a magnesium oxide, bimetal oxide of aluminum and cerium, and titanium-based nanomaterials, and hydrous cerium oxide. However, drawback of these adsorbent can come from the regeneration, low absorption capacity, and low study of kinetics. Now, different parts overall the world have high concentration. So it's very important if we test our nanomaterial to eliminate fluoride. By estimating the maximum absorption capacity, we compare the bimetal oxide and the core shell nanomaterial, as we can see from this figure, as a relation between the equilibrium absorption capacity and the residual concentration of fluoride. Using the bimetal oxide, we obtain higher than 40 milligram per gram of fluoride removal. And impregnating of fluoride led to enhancement of the maximum absorption capacity, as we can see, higher than 90 milligram per gram. Applying different isocell models, such as Langmuir, Flinders, and Dublin, so we obtain maximum absorption capacity using the bimetal oxide 44 milligram per gram, and 91 milligram per gram using the magnetic core shell nanomaterials, and using the another isotherm models, which is Flinders. Due to the n values here higher than 2, so we have an estimation that physical absorption mechanism of fluoride with the core shell nanomaterial. Confirmation of this using the Dublin isotherm models, we have an apparent energy when this value lower than 8 kilojoule per mole, so we have a confirmation that physical absorption mechanism between the fluoride and our core shell nanomaterial. What could be the mechanism of interaction here? Can be into two steps. First one, a hydrolysis of the core shell nanomaterial. The metal ion correspond to the iron or cerium and titanium. And the second part, an ion exchange between the fluoride ion with the hydroxide. As a third step, as I mentioned before, our objective of any nanomaterial is a regeneration study. We did an optimization for the regeneration study by testing two concentration of sodium hydroxide. Low concentration as 0.1 molar and 0.5 molar. And as we can see, 6 hours using high concentration, we can achieve around 95%. And by low concentration of sodium hydroxide and prolong the time, we obtain around 98%. We could recover our nanomaterial for the reusability study. Applying 5 adsorption-desorption cycles, which is a relation between adsorption capacity and cycle numbers, and also the percent recovery, we obtain our nanomaterial could be applied for 5 cycles with a low decrease in the absorption capacity. It's very important now to know an information about the stability of our nanomaterial, if it stays the same or something changed. And especially when we are talking about our nanomaterial which contains cerium. Cerium ion has a toxicity, so it's very important to know this information. Characterization after the 5 absorption-desorption cycles and using the transmission electron microscope, we obtain high aggregation of our core shell nanomaterial and also losing of the crystalline structure. So now we have like an idea that our nanomaterial is a change, but we don't know if they change from the core shell or to mixed oxide or still the same. So we did another characterization using the scanning transmission electron microscope. As we can see, we didn't see well as the core was coated with a shell nanomaterial. And the confirmation with a scanning ion profile, as we can see, all the 3 metal ions are in the center, which means in this case, our core shell nanomaterial changed from core shell structure to mixed oxide. Cerium ion, it's very important to know about after changing the core shell nanomaterial now. So we did an analysis using the ICP, and we have a confirmation that we have a cerium release about 12%. So it's very important to know the cerium release, which will be the source, if in the treated water or the dissolving solution. So we analyze both. After the first cycles and the fifth cycles, we didn't detect any cerium. So now the cerium release will be in the dissolving solution, which is the sodium hydroxide. And we have a confirmation about increasing the cycles led to increase of the cerium. So in this case, our nanomaterial could be applied, but further study is needed to optimize the regeneration study. Another parameters as an effect of pH, we obtain by increasing the pH value lead to decrease the absorption capacity due to the competitive between the hydroxyl ion and the fluoride. And another parameter as a temperature, we obtain at 30 degrees Celsius, we have a high absorption capacity. Applying our core shell nanomaterial into a real drinking water, which is from the department, but fortunately, we didn't find any fluoride in the drinking water of the department, but we did on a spike of 10 milligram per liter to obtain an information what could be the effect in the presence of other ions. And after applying the absorption process at 25 degree and 30 degree, we obtain a residual concentration of fluoride lower than the maximum contaminant level. So this means our nanomaterial could be applied into a real drinking water. Conclusion of this work, maximum absorption capacity is 44 milligram by using the bimetal oxide and 91 milligram per gram by using the core shell nanomaterials. Absorption mechanism could be as a surface ion exchange between the fluoride and the hydroxide, and no serum release in the treated water, and lower than the maximum contaminant level after spiking with 10 ppm of fluoride. And these results have been published in the Science of the Total Environment. The second, for the core shell nanomaterial, we already start for phosphate removal using the core shell nanomaterial, but we didn't finish it until now. But we are thinking also to try to remove phosphate using another support as a cationic exchange polymer. So the phosphate removal using the magnetic nanocomposite of immobilized magnetite nanomaterial on a cationic exchange polymer, this work has been collaboration with the Department of Mining Engineering and Natural Resource, OPTA. What could be the sources of the phosphorus contamination? Could be from the municipal wastewater, which is a vary from 4 to 15 milligram, industrial wastewater higher than 30 milligram per liter, domestic wastewater from 10 to 30 milligram per liter, and treated sewage wastewater from 1 to 5 milligram per liter. And our target will be, in this case, lower than 0.50 milligram for drinking water as a guideline standard. Which method we use to synthesize this magnetic nanocomposite? This type of nanocomposite based on two methods is a combination between intermatrix synthetic method coupled with a co-prestation method. First, our cationic exchange polymer, which is coated C100, as we can see like a yellow color, has a function group of sulfonate using the intermatrix synthetic method and in the presence of iron 2 and iron 3. So now we have an exchange between the sodium and the iron, and applying the sodium hydroxide for the co-prestation method, then we obtain the cationic exchange polymer coated with a magnetite, and the confirmation of this immobilization from the black color as we can see. For the phosphate removal, we already did like a different loading of iron in the cationic exchange polymer, and as we can see, by increasing the loading concentration led to increase the thickness of the bright here. And comparing this bright with the polymer without nanomaterial, so now we have a confirmation that the magnetite immobilized on the surface. To obtain another information, if we have the iron on the surface only or inside, we made like an iron profile, as we can see the iron which is correspond to the red line here only on the surface. Using the transmission electron microscope, we obtain around from 15 to 20 nanometers of magnetite and crystalline structure using electron diffraction pattern and the highly magnetic properties by applying permanent magnets. Here in this case for phosphate removal, we used another method, which is a fixed big column, by passing an eluent of 10 milligram per liter of phosphate using pre-static pump in a column which contains the absorbent of the nanocomposite and analyzing the air effluent of phosphate using the biosystem analyzer and the ionic chromatography, and the optimization by first of all effect of pH, we obtain at pH 7, we obtain high absorption capacity. Estimation of the maximum absorption capacity, we apply two pH values at pH 5 and pH 7. And as we can see from this figure, at pH 5, we achieve here a saturation which is higher than or around 3 milligram per liter, and the maximum absorption capacity by applying azimuth models is 2.8 milligram per gram. And at pH 7, we didn't achieve any saturation, so the maximum absorption capacity here is higher than 4 milligram per gram. And from the modeling, we estimate we have a complex formation mechanism between the magnetic nanocomposite and the phosphate. The third part, for the regeneration of this magnetic nanocomposite, we apply different concentration of sodium hydroxide, and we obtain at 0.5 molar of sodium hydroxide high recovery of phosphate. Then for the reusability study, we apply our magnetic nanocomposite up to 7 cycles, and only we can see after the first cycle a decrease in the absorption capacity and then maintain stable. So it means we can use our magnetic nanocomposite for 7 cycles. Comparison of the efficiency of our nanomaterial with another absorbent in the literature, what we can see, we have absorption capacity here at pH 7, which is higher than other for the magnetite or another iron-based nanocomposite. However, we have a low absorption capacity regarding to the zirconium oxide, but our nanocomposite had an advantage comparing to this material due to the highly cost and the no regeneration study have been used using these nanomaterials. So conclusion of this work, by applying different loadings, the optimum concentration for phosphate removal was 23 milligram iron per gram nanocomposite. High absorption capacity was found at pH 7 comparing to 4, 5, and 6. And the maximum absorption capacity at pH 5, 2.8 milligram per gram, and higher than 4 at pH 7. And 97.5% recovery using 0.5 molar of sodium hydroxide after 3 consecutive cycles. And we could use this magnetic nanocomposite for 7 absorption-desorption cycles. And these results have been published in Environmental Technology. And another publication for this in Industria Chimica. Last part, for the optimization of the harvesting efficiency of sedimentous microalgae using a low cost of magnetic-based nanomaterials. This work was performed in a collaboration with a group of environmental engineering and microbiology, OPC, and another group de biodegradation de contaminant industrial y valorisation de résidus, OAV. This work also has a premio 2017 por the Días de la Charcha de Referencia en Biotecnología. Several methods have been used for harvesting of microalgae. The drawback of the main method, or this as a centrifugation, chemical flocculation, and bioflocculation, came from this drawback from the high cost, cell damage, biomass toxicity, and only 50 to 60% biomass recovery, and also for the slow process. Another new technology to optimize or to obtain high absorption capacity, to obtain high harvesting efficiency using the magnetophoretic separation, which is advantage of this, the low cost and time saving. So from this part, we are thinking to synthesize different nanomaterials which contain positively charged. Why? Because the microalgae had negatively charged. So we synthesize a magnetite with a positively charged in the presence of surfactant, cationic surfactant, and to enhance the positively charged by using another surfactant as a shell material and by using another polymer as a polyethylene imine. Characterization of these types of nanomaterial by using transmission electron microscope around 11 nanometers, and with the shell of the CTB and PI around 1.65 nanometer as a shell of CTB and around 0.86 nanometer as a shell of polyethylene imine. And all of these nanomaterial have a crystalline structure. We did a screening of these nanomaterial for the harvesting efficiency of the microalgae, and we obtained higher than 82% removal of or separation of the microalgae from the wastewater or from water. This magnetic separation after 20 minutes by applying permanent magnet, we have a confirmation here higher than 82% of the separation. Confirmation if we have inside or outside our nanomaterial with the microalgae. We did a characterization using a scanning electron microscope, and from this SEM image, we have a coverage of a magnetite on the surface of the microalgae. And using transmission electron microscope, we found that we have inside and outside the microalgae. Optimization of this harvesting efficiency, we are using central composite design with a response surface methodology by applying two parameters, a magnetic separation time and the amount of the magnetic nanomaterials. And what we can obtain here, as we can see from this figure, until 5 minutes, we didn't find like an increment of the harvesting efficiency, but increasing the time we obtain around optimum around 13 minutes, and increasing the dose or amount of magnetite led to increase the harvesting efficiency or the removal percent of the microalgae. But further study for this optimization will be performed with another new master student. Will be start from with our group. Estimation of the maximum absorption ether using the magnetite iron oxide, the magnetite nanomaterials. What we can see higher than 2.5 milligram per gram dry cell weight per gram nanomaterials, and applying different ether models as a Langmuir, Friendlich, and Dubinin, we obtain maximum absorption capacity of 3.49 gram dry cell weight per gram nanomaterials, and from the N value as a Friendlich here, lower than 2, which means we have a chemical interaction between the microalgae and the nanomaterials, and another confirmation is the Dubinin model from the E value, which is now is higher than 8 kilojoule per mole. So we have a confirmation that we electrostatic interaction between the microalgae as a chemical interaction. Confirmation of this by using the zeta potential technique. We have a negatively charged of microalgae and the positively charged. So now we have a electrostatic interaction between both as an absorption mechanism. Regeneration study for these types of nanomaterials, we have been used here couple of the detachment method by using ultrasonication method and alkaline condition. And when we are applying this method for the reusability, we can see from this figure, we can use our nanomaterial for 6 cycles without any decrease of the harvesting efficiency. So we can use our nanomaterial for the harvesting efficiency of the sedimentants. So conclusion of these parts, higher than 82% of microalgae could be harvested using magnetite-based nanomaterials. Magnetic separation time is a significant factor on the removal. And monolayer absorption with a maximum absorption capacity, which is 3.49 gram dry cell weight per gram nanoparticles. And we can use our magnetite-based nanomaterials for 5 absorption-desorption cycles. And these results are in preparation to submission. The second part of our work, which is mainly for the gases treatment, is divided in 2 main parts. The first one for the catalytic oxidation of carbon monoxide by encapsulating cerium oxide with gold into metal organic framework for carbon monoxide oxidation, and second one for the methane absorption with the modified polyurethane sponges with the magnetic nanomaterials by using Crustacean method. The first one, this work was performed in a collaboration with ICN group, and they already synthesized and characterized this metal organic framework. So here our objectives to obtain or to estimate an information about this nanomaterial if it less than 200 degrees Celsius and comparing with the literature. And if this nanomaterial have a catalytic oxidation lower than 200 degrees Celsius, so this nanomaterial could be applied for the catalytic oxidation. Here in this study, we used the fixed big column by using a cylinder which contain a mixture of gas of carbon monoxide, oxygen, and nitrogen, and passing through a column control temperature in an oven, and analyzing the produced carbon dioxide. using the gas chromatography TCD detector. First, we did a test of the organic framework or the organic beads without any nanomaterials. From this figure, as we can see, as a relation between the conversion percent versus the temperature, using the organic beads without any nanomaterial, we obtain the 100% conversion at temperature 440 degrees Celsius. And by encapsulating the nanomaterial into the organic beads, we would like to see if we have an enhancement or inhibition. What we can see by different loading, different weight percent of the nanomaterials into the organic beads led to the enhancement of the catalytic oxidation. For the 2.8%, we obtain 180 degrees Celsius for 100% conversion. And increasing the weight percent to 5.5, we obtain 110 degrees Celsius for 100% conversion, and increasing to 7% led to 100% conversion at 100 degrees Celsius. What could be the stability of this material, if it's stable or no? So we did 3 cycles, and we obtained, as we can see from this figure, we can use this nanomaterial for 3 cycles without any loss for the material. And another study for the stability, by prolonging the time until 50 hours, we have an stable material without any loss of the efficiency. Another parameters that we estimate from this material by calculating the turnover frequency, which is the most important parameters to obtain about the efficiency of the catalyst, and by testing at 4 degrees, 30 and 50, 75 and 100 to increase the turnover frequency, and calculating the activation energy, we obtain 40 kilojoule per mole. Comparing this material with another from the literature, as we can see, our material here high efficiency with low temperature less than 200 degrees Celsius, as we can see for 7% 100 degree, and 5.5 at 110, and for 2.8 180. So conclusion of this low aggregation of nanomaterial by encapsulating into the organic beads, 50% conversion was obtained at 72 degrees Celsius and 100 degree for 100% conversion using 7 weight percent, and low carbon monoxide conversion by encapsulating this nanomaterial into the metal organic frameworks, and this result has been published in Journal of Material Chemistry A. The second part for gases treatment is methane absorption with the modified polyurethane sponges with a magnetic nanoparticle synthesized by chemical post-station method. And this work was developed in the framework of the project of NanoChay, founded by Aresis. As I mentioned before, the global climate change could be due to the increase of the greenhouse gases. So in this part, we selected one, which is the methane, and by testing the magnetized nanomaterials immobilized in the polyurethane foam to see if it have efficiency for the absorption or not. So synthetic of this material, we have the polyurethane foam, which have like function group of amide. And then first we cutting these sponges into dimension of 0.6 and 1 centimeter. Immobilizing or loading with 2 concentration of iron 2 and iron 3 and applying Crustacean method. So we obtain 2 protocols coded with A and B, and what we can see, we have a magnetite into the POV by changing the color. Characterization of this nanocomposite using the ICP. For the A, we obtain 4 milligram iron per gram nanocomposite, and for the second protocol, 8 milligram iron per gram nanocomposite. For this study, we used the fixed bed column by passing an inlet of methane through a press static pump over the adsorbent which contains the nanocomposite, and then analyzing the air effluent using gas chromatography flame ionization detector. Characterization of this nanocomposite using the transmission electron microscope, we have an information that immobilization of the magnetite on the surface of the polyurethane foam with an average size of 87 to 108 nanometers, and From these EDS spectra, we have a confirmation that we obtain iron and oxygen and the crystalline structure using the electron diffraction pattern. Maximum absorption capacity estimated using the polyurethane foam and comparing with another which contains the magnetite with two concentrations. So first we did an absorption isotherm of the POF without any nanomaterials, and as we can see, maximum absorption capacity was higher than 550 milligram per gram. And most important to know if an increment or increase absorption capacity by impregnated zinc magnetite or no. Testing the absorption capacity with a low concentration, as we can see, enhancement of the maximum absorption capacity, which is higher than 650 milligram per gram. Increasing the concentration of the iron into polyurethane foam led to increase the maximum absorption capacity, which is higher than 750 milligram per gram. Applying different isotherm models of 2 parameters, 3 parameters, and the combination between the 2 and the 3. So we obtained best fitting due to the R squares using the combination here, due to the R square higher than 99%. And we estimate the maximum absorption capacity using polyurethane foam without nanomaterial to be 639 milligram per gram and A 726 milligram per gram, and with the protocol B 796 milligram per gram. Comparing this absorption capacity with another adsorbent from the literature, as we can see, our nanomaterial have high absorption capacity comparing to others. One of the advantage of our nanocomposite comparing, for example, with the MOF 177 is the highly cost of the MOF due to the presence of our nanomaterial of a magnetite, which has a low cost nanomaterial, and another advantage of the presence of magnetite that could be easily separated and then we can reuse it again for adsorption of methane. So we did a regeneration by passing a nitrogen and testing the reusability up to 5 cycles, and we obtained 5 cycles of adsorption of methane with a stable of adsorption capacity. Conclusion of this work: high concentration of iron led to high adsorption capacity. Maximum absorption capacity of methane was found to be around 800 milligram per gram using protocol B, and 726 milligram per gram using protocol A, and 639 milligram per gram using POF without any nanomaterials. And this structure was proved to be highly stable and could be applied for 5 cycles. And this nanocomposite is highly competitive comparing to another adsorbent from the literature. And these results also are in preparation for submission. So as general conclusion from this work, first one, different nanomaterials have been synthesized and characterized. Magnetic core shell demonstrated high efficiency for fluoride removal. Magnetic nanocomposite was demonstrated for the phosphate removal. Higher than 82% was proved using the magnetic-based nanomaterials. Gold cerium oxide encapsulated into metal organic framework was proved to be highly efficient for 100% conversion for a temperature lower than 200 degrees Celsius. And lastly, high absorption capacity of methane was proved using magnetic POF nanocomposite. Future work from this: for a study of the effect of coexisting ions for rare water matrix, detailed information for the kinetic study, evaluate the efficiency of our core shell nanomaterial in a fixed column instead of a batch, enhancement the properties of the core shell nanomaterials to obtain high removal for anions as well as heavy metals. Scale up the system is needed to investigate the efficiency of the adsorbent, and study the life cycle assessment of the nanomaterial, and more information of the toxicity of this nanomaterial to the environment is needed. Thank you so much. And if the committee give me a chance to read the general conclusion.
I think it's not necessary. It was clear with the presentation. Thank you. Take 1 minute to recover. I think it was fast either for me. That is. Then after this nice presentation, and fast also, and heavy like the material right here, and we are going to move to the question for the committee. We will start with Dr. Ponsan.
First of all, I would like to congratulate you, Ahmed, because as Javier mentioned before, the presentation was very nice, but so the amount of work that you have done in this PhD thesis is huge and also impressive. So congratulations for that. A few words in Catalan. M'agradaria també agrair al grup dels directors de la tesis, al grup de compostatge per haver-me donat l'oportunitat d'estar aquí en aquest tribunal i per sempre és molt agradable tornar a casa, encara més si ho fas invitat pel grup on vas néixer científicament. Moltes gràcies, de veritat. Well, Ahmed, after these words, I would like just to start with some comments. So I will do some comments about the format of the document, and then I will go for some general comments about the content and also some specific issues. So at the beginning, so when I received the PhD thesis, as Javier mentioned before, it was too heavy. So like, wow. And in fact, the weight of the thesis corresponds to the real work that you have done. That's a direct correlation. And I think that, well, there are a lot of information, and sometimes it's not easy to read and understand everything. I like the format you have prepared, because you have a general introduction, you have a general materials and methods, but then in each chapter of results, you have again an introduction and a general method. So it makes easier to follow the thesis, but sometimes I also had the feeling that I was reading again and again the same many times. But this is, well, it's a good point, but also a bad point, because at the end I have the feeling that I have read this 3 or 4 times before in the PhD. But apart from that, and again, another comment about the format. So you have high quality pictures, figures in all the PhD thesis, unless in chapter 9. I don't know why, because then in the paper you have again high quality figures, but when you go to this document, it's something that, well, it's different, and it's nothing. It's just a comment. Okay. And also another good point of the thesis is that you have used a lot of references, and well, it makes also easier to follow everything. We are moving about the content now. Now we will start interaction. I will go directly to chapter 4, when you are carrying out just the first screening and assessment of the possible environmental uses of the nanoparticles. And in table 4.1, where you are summing up all the results obtained in the beginning of the chapter. At the end, when you are discussing that results, you said that an optimization and the best results are obtained when using a mixed oxide. Let's see. I am right? Yeah. But in fact, what you are doing using the mixed oxide is just, are you taking the same amount? Are you summing the amount of the cerium and titanium oxide? And in fact, if you can compare the single absorption of the cerium and titanium, the mixed oxide results are lower than the ones that you obtain using the single titanium oxide or the single cerium oxide.
Yeah, this is why we are thinking to obtain using the single nanomaterial as a cerium and titanium and magnetite. So we are thinking how to obtain one nanomaterial by using the same amount without any mixing, to obtain one nanomaterial and to estimate the efficiency, as I explained for the next part, as a core shell nanomaterial.
Okay. And another question in relation to that, why are you using that concentration of phosphate and nitrate? Why do you choose that ones? Because then, if we don't have any isotherms of absorption, and why did you choose that ones?
Yeah, as example for fluoride and nitrate, according to the maximum contaminant level, which is 50 and 44 milligram per liter, So we choose this concentration according to this guideline to estimate what about the efficiency of this metal oxide nanomaterial.
And do you think that you can reach the discharge concentration levels? I mean, for phosphate and nitrate, so the 2 ppm or 15 ppm?
To prepare?
If with this kind of absorption, using that, because we have just a single point, no? And you have a percentage of removal.
Yeah.
That's a percentage, but do you think that you can use this kind of nanoparticles to reach the discharge levels that will be required to discharge the effluent?
Yeah, this, as I mentioned, by using the metal oxide nanomaterial, such as like aggregation. So we are thinking if we have like efficiency of this nanomaterial. So first study for the optimization process, as I explained in another chapter for fluoride and phosphate. So the first part of the chapter 4 is like only a screening. If this material have efficiency, potential efficiency or no. And if have a potential efficiency, which type of metal ion in the nanomaterial could be high removal for these pollutants.
I know that we cannot ask you more work than the one you have done, but I'm quite sure that here the isotherms will provide a lot of information, because now you are quantifying the absorption capacity.
Yep.
But what is the maximum absorption capacity? Because you are having, in some cases, the removal efficiency of 100%. So then I guess that the absorption capacity is underestimated in that cases. Yes. So in this cases, the absorption capacity is high, but underestimated for sure, because this is not the maximum.
But as I mentioned also for this part, for sodium oxide or titanium and magnetite, in some of them for the contaminant removal already in the literature. So we would like to optimize and enhancement of this absorption process or for even any contaminants. So our target to obtain which nanomaterial we could apply for several contaminants, and then synthesizing one nanomaterial to be efficient for water contaminants removal for several contaminants, not only one. These were our objectives.
Well, thanks for the answers. I'm moving to chapter 5 now. So in previous chapter, you determined that the best pH was 5. In chapter 4.
Chapter 5.
In chapter 4, you determined, so you were comparing the absorption efficiencies and the removal efficiencies different at pH 5 and pH 7.
Yeah.
So the best efficiencies are obtained at pH 5. And then we move to chapter 5 and you start working at pH 7. Why?
Because the real pH medium is a pH 7.
And you are not considering the modification of the pH of the medium if you are obtaining much higher removal efficiency?
Yeah, but as we can see, by applying the effect of pH using the Corshell nanomaterial, we have a wide application for the pH range, which we can use with a stable nanomaterial for the removal efficiency of fluoride, as example. So our Corshell nanomaterial was stable for a wide range of pH. So even for pH 5 or pH 7, we have high efficiency.
So it will be possible to use pH 5 and have a higher.
Yeah.
And in chapter 5, what did you decide? I'm sorry for asking this again, but what did you decide to use the 50 ppm of nitrate?
Because as maximum contaminant level.
Yeah, this is the maximum, but this is the this is the boundaries, the limit. So this is the if you want to consider drinking water, it should be under this level. So,
yeah, it should be under.
Yeah. So why we want to apply this technology to reduce the concentration of nitrate if you are already under the level?
Yeah, because as a first step, we would like to see if our nanomaterial in the limit have efficiency or no. And if it's have efficiency, so further optimization will be like by doing an absorption isotherm.
Okay, and another question is like, considering the previous work that you have done in chapter 4, that should be used to compare the results with the next chapters. Well, in chapter 5, when I read this, at the end I said, okay, let's compare these results with the ones obtained in chapter 4. But I couldn't because the test conditions are not the same and the concentration is not the same. So as I don't have the isotherms, and I cannot compare. So I don't know if it's better or not, or the question is, why did you don't use the same conditions in order to be able to compare the results of obtain?
You mean in this case by doing adsorption isotherm using the magnetite as a single cerium oxide and titanium oxide? But as I explained, in this case, our target to obtain a nanomaterial with high adsorption capacity, and also for the regeneration that we can use this adsorbent for several cycles of desorption, because from the literature, by using cerium only or titanium or magnetite, there is a lack of information about the regeneration study, as example, or low absorption capacity. So we focus about this nanomaterial and testing for different parameters, as estimated of maximum absorption capacity, and what about the regeneration study and the reusability.
Well, I think that to have here the isotherms it will be fantastic, because it will provide the whole results that you need to analyze and compare with other kind of. But as I told you before, you have done a lot of work. So
it's fine.
Well, and if we move to chapter 5, here you have all the absorption profile. So it's isotherms. I mean, so this is something that, well, it provides us much more information and allows us to have to understand much better everything. In chapter 7,
yep.
If we just have a look, or our focus, so we are dealing with the phosphate removal.
Yep.
Yeah. If we are here, we consider the effect of pH. It has a total inverse opposite effect than in chapter 4. So in chapter 4, when we reduce the pH using magnetite, so the efficiency removal was increased and the absorption capacity increased. Here is just the opposite behavior. Why?
Yeah, because sometimes when we immobilize magnetite, as example in our work for the phosphate removal with the cation exchange polymer, sometimes the nanocomposite or the nanomaterial change the properties. So it depends. Any adsorbent has a characteristics and for application. Sometimes we can find like a magnetite itself has a high efficiency at pH 5 compared to pH 7, and when we immobilize with another supports, as example as the cation exchange polymer, so the properties can be changed, as we found.
And why did you have not considered the graphene or nanotubes as a fixed material for the magnetite?
Yeah, we are thinking for this, but the time is not enough.
Yeah, I know. But when I was revising the literature on that, so I realized that there are a lot of emerging publications that stating that this is obtaining a very good absorption capacities and efficiency removals on that. Well, and as you have tested a huge amount of nanoparticles in the composites, I expected when I was reading it, I will find this. I didn't find it.
Yeah, it's a great idea, but the time is a problem for time.
I'm just asking if you have considered this or not, and obviously you don't have time to do everything. But something that we can do. Why did you? What do you think that are the reasons to obtain a much better absorption capacity in the previous assessment done in chapter 4 than in this work? So, for example, in the chapter 4, you reported absorption capacity at pH 7 or 5.7, and here the one you're obtaining is 2.8. What can be the reasons?
The reasons of this.
Sorry?
The reasons of the maximum absorption capacity comparing to pH 5 and pH 7?
No, I mean when you have the magnetite, you assess the capacity of magnetite to absorb the phosphate in chapter 4. So the first segment, you obtain an absorption capacity at pH 7, which is the same pH here, of 5.7. Here, when you are trying to improve the removal of phosphate with this nanocomposite, the absorption capacity is 2.8.
At pH 7,
pH 7
higher than 4, because as I explained from the figure, we didn't achieve the saturation.
Yeah, but I mean comparing the magnetite with the nanocomposite.
Yeah,
the same.
I understood. At pH 7, as example in chapter 4, absorption capacity under equilibrium 5.5 as example, and comparing with the nanocomposite under the same condition of pH 7, we didn't achieve from the absorption alternate the maximum absorption capacity. So as I mentioned, it's higher than 4. If we are applying another initial concentration of phosphate, we can obtain the same concentration of the maximum absorption capacity.
Great. In chapter 10,
yep.
You explained that the absorption of methane is carried out using nitrogen. Nitrogen. And I would like to ask you, if you carrying out this desorption process with nitrogen, are you going to be able to recover or energy or wherever from this effluent? I mean, from the methane, because I wasn't able to determine what would be the concentration of methane in this effluent. I mean, the nitrogen one, because you have 40 minutes of 0.5 milliliters per minute. So that means that you have 20 milliliters of volume of nitrogen and methane. Yep. But was the concentration of methane in this effluent will be enough to valorize this methane, or what are you gonna do next with this effluent?
Next, in this case, for the effluent of methane, to determine the concentration based on the sensitivity of the detector. So if we have a low concentration of methane, we can use the TCD, as I mentioned. We can determine ultra-trace concentration of methane. But for further study for this effluent of methane, it's need like further study. Needs further study to measure the methane and what could be low or high, and if it at 40 minutes it's enough for this, or it's less to optimize. Another optimization, what I mean, for this desorption study of methane.
But do you think that it's going to be possible to valorize the methane after the desorption?
It's like in a complex system, but it could be. It's interesting to do it if we can valorize it after the desorption study.
I mean, you are absorbing the methane,
yeah.
Then you are desorbing the methane,
yeah.
And what are you doing next with the methane?
With the methane, we can apply for methane storage, as example, using this nanocomposite, or for transportation, or we can use this nanocomposite for the methane produced from biogas, from anaerobic process. So we can apply it in different fields.
Right. I am just worried about the percentage of methane that you will have in this effluent, because if it's, I guess that it will be low, it will be difficult to valorize from an energetic point of view, but for sure you are in a starting point of
yes.
research. And in this chapter also, in the pages 266 and 270, when you are comparing the absorption capacities of nanocomposite A and B and just the polyurethane, why you don't consider just the use of polyurethane for the absorption if you have extremely high absorption capacities with that? Maybe improving a little bit the shape and the area of the particles will be enough, because the increasing of absorption capacity with the polyurethane and polyurethane plus the nanoparticles is not a lot. And I'm just, because we will talk later about the cost effectiveness of the technologies, but if talking about now, specifically in this case, about the cost effectiveness of this nanocomposite,
yep.
You think that will be, from the economic point of view, much better to optimize just the polyurethane absorption rather than the polyurethane plus nanoparticles?
Yeah, this one is a great question, but we think in this case, by using the magnetite immobilized in a polyurethane foam, we can have like enhancement of absorption capacity, and also in terms of the magnetic separation due to the magnetite presence, so we can separate this from the media and then we can reuse it again. But without magnetite, it's not so easy to separate it from the medium.
Yeah, and nanocomposite A and B, they have similar absorption capacities. B has higher one, but in fact, the nanocomposite B has almost the double iron concentration. So do you think that even the nanocomposite B is the best one, considering that you have double the iron concentration, or you will go for another one, considering the cost effectiveness?
For the cost effectiveness, it's much better if we have another study to increase. But in terms of the cost and the aggregation of the nanomaterial, it's much better if we are using low concentration of iron. in terms of high concentration of iron.
Yeah, that's why I'm asking you this, because so you are choosing the nanocomposite B.
Yeah.
It has the almost double concentration of iron than nanocomposite A, and
yeah.
the absorption capacities are similar.
Yeah, it's a little bit higher, but with a little value. But we are thinking this is the maximum absorption capacity. But you are right in this case. If we are using low concentration, which be much benefit with in terms of low aggregation and for another cycles. Yep.
Yeah. I have now some kind of general comments. Yep. Because yeah, it's true. Because so I had when I started reading this, so the first question I wrote was, why you are not assessing the possible interactions with other ions or with other particles, because in real wastewater you will never have just a single. Yeah. And when I arrived at the end and the future work, the first sentence you wrote is, okay, this is what I expected. But as the question was already written, so I'm I'm asking you this. So what kind of influence do you think that it will have on the absorption capacity of your nanocomposite nanoparticles, the presence of other kinds of ions or suspended solids or organic matter in the matrix? What kind of influence? And
which nanoabsorbent, which absorbent nanomaterial?
Wherever. So in wherever nanoparticle or nanoabsorbent nanocomposite that you are going to use to remove some pollutants, yeah, you will never find a single pollutant in the solution. Yes. It's going to be a complex matrix with suspended solid, organic matter, another kind of ions, cations, and so what kind of influence it will have to your absorption process, cost effective?
In cost effective, in this case, by applying the study of the coexistent ions. For example, when we tested the core shell nanomaterial, we demonstrated the removal efficiency of fluoride and also phosphate in the presence of phosphate, and for chloride and sulfate, and the negatively effect, as example, as I remember, for sulfate. So in this case, another study for the effect of each ion, if we have like a dual interaction between in the presence of other multi-component, or in one single, for example, fluoride and sulfate only, or fluoride, sulfate, and phosphate. So this means that I mentioned needs further study to know information what could be for the application.
Have you thought about what kind of measures are you gonna or can you implement in order to favor the absorption of the target pollutants in each case? So have you thought in any kind of strategies in order to favor just a single absorption of a single component? The one is the one targeted in each case. I know that it's not an easy question.
Yeah. It's not easy to do something like that, but we are thinking if we are using, as example, the center composite design by studying the effect of each parameters of each ion and the removal by using this adsorbent to have an information what could be the optimum in this case.
Another question related to that one, I have just a couple of questions. Another question related to that is, I'm not an expert in this field, obviously, but do you think that will be possible to express the absorption capacity in another units that will make you know the amount of particles, molecules of the pollutant that has been absorbed in a certain amount of absorbent? So you can just express the absorption capacity in other units?
It could be after the analysis using the ICP, so we can express the absorption capacity in terms of, as example, for iron or cerium and titanium. But in a real case, for all of the nanomaterial, not only one.
So my question was related because maybe if we express the absorption capacity, apart from expressing this in milligrams of absorbate per grams of absorbent, this is but if we can express this data in moles of absorbate per gram of absorbent, so if you have the mole amount, in fact you are having, you know the amount of particles that has been absorbed, this amount. So you can correlate the amount of particles of each pollutant that has been absorbed in a surface of the nanocomposite or whatever. Yeah. So I mean, so it will, for the future work, and I repeat, I'm not an expert on that, I think that will be nice, or will be useful to know the amount of particles of each pollutant that has been absorbed in a nanocomposite or whatever, and the units that will allow you to know that is expressing the absorption capacity in moles of absorbate per grams of
in moles.
Moles, in fact, is the number of particles.
Yeah.
Number of particles of a specific pollutant. So then you can know if after being absorbed a certain amount of an anion, still you have room for absorbing another amount of another kind of anions. Well, we can discuss about this later. Yeah. Another general question they have. Well, you described since the very beginning the nanoparticles absorption technologies as a cost-effective, and you mentioned this several times in the document. And I have found one reference in page number 11 that refers to a publication of the year 2016. But if you go to this publication, then you directly and literally go to a reference from the 1995 from a Hungarian pollution and effects on health consideration. And this is where you have reference that the absorption, nanotechnology absorption, is the most cost-effective technology. I'm guessing if after 22 years of this reference, the other technologies have advanced also, and I don't know if because I have not found any economic analysis of it, although it was an estimation, but I have not found any economical cost analysis that make me just write 100 times here that absorption nanotechnologies are the most cost-effective rather than the others, because I cannot compare. And if I have tried to search this reference, and so I went to 1995, and well, I said, well, I rely on you, but I would like to see something that I thought it was an estimation.
Yeah, an estimation, especially from the literature, due to the presence of iron in the nanomaterial, means that here in this case the cost-effective material. But in the presence, as example, of rare earth metals such as titanium or cerium, make the process costly. So from the literature, they are considering the iron, which is a low-cost material.
But also in terms of the other technologies, well, the ones that are based on membrane, but the others electrodialysis, and all these technologies has advanced a lot. And in fact, now they are implemented at industrial scale to remove this kind of. If they implement it, it's because the cost effectiveness has improved a lot, because a few years ago they were not. So maybe it will be great to have current, present economic analysis to confirm that you are working in the most cost-effective technology. And the last one is quite general. It's like, what do you think that are the bottlenecks to scale up these technologies?
To scale up this technology, it's not so easy. It's like a complex, because when we are thinking to increase the preparation or to synthesize high amount of nanomaterial, it's not so easy, because sometimes you can have like a different properties of the nanomaterial, and even more parameters should be optimized for the scale-up process. So it's another study. It's not so easy to follow. Yeah,
I guess that you have many bottlenecks, many district lab, and I think that I will finish with that. I would like to finish again, so giving you the congratulations, because so you have a lot of results, you have high quality results. We know, everybody knows that you have worked a lot, and well, another work is here. You have 5-6 papers already published, right? Yeah. And a couple of them are under preparation already.
And another not prepared.
Well, that is another well, point to be congratulated, because it's impressive. Well, I would like to say well, it's not just your work, it's also the work of your supervisors, and also you cannot do for sure this amount of work without a powerful group behind you, so these congratulations are extended to the whole group and the supervisors. And that's all from my side.
Thank you, Dr. Punsa. Now have the word, Dr. Macanash.
Okay. Thanks for this introduction, Mr. President. Thank you for asking many of the questions I've already prepared, so I will be short in my participation. And first thing is just to congratulate you for your work, and congratulate your directors and supervisors for supporting this candidate which now is close to be doctor without any doubt. I would like to congratulate you because this is the example, paradigmatic example of what a candidate for the PhD has to do. So it includes bibliographic research, synthetic procedures, characterization techniques, analysis of different substances, absorption experiments with, how to say, seeking amount of work. Just, I think, I wonder why you are not ill, because there's it's too much. And what is also very important, and it's a proof of your value and the value of the group and supervisors, is the redaction of many very interesting and high valuable articles we have been published in international journals. So just I could finish my intervention here and saying congratulations, but I'm not going to do it. Okay? So I'm not going to do it because I think this is a thesis that many other people, maybe some of them here in the audience, can use for writing their own thesis, but there are some things to be improved. Okay, so I want to say also them, because it's not perfect, it's excellent, but some mistakes are here. Well, first, the redaction is in English better than mine, so that's very, very few to say. But I found some sentences without verb. That happens. Okay. I also found some equations which are not correctly explained, like the Dubinin-Radukshevich isotherm. There's some mistakes in the explanation of the terms, but these things happen. And also in the structure of the thesis, okay, annex is at the end, introduction at the beginning, but the outline is in chapter 3. So that's quite strange. The outline could be perfectly in the foreword or in the introduction. So when you arrive to chapter 3, then you explain what chapter 1 is. That's quite a strange thing. That could be improved for other students to do it. There are also little mistakes, like the now synthesis of sulfur hexafluorocarbon, which is not an existing compound. Okay, and some errata in this writing of some words. That's not so much problem. I would like to emphasize the accuracy of the description and measures of many of your results, but also I will say that the error of some of the values is not so much correct, because you are giving too many figures. I mean, after the comma, when you are saying that something is 50.03 plus 2, there's no many sense in that. So that could be corrected for the future students to present. And in particular, when you talk about the size of nanoparticles, one I remember is like the 13 plus minus 177. So that means that you are measuring less than angstroms.
In this one, using the ImageJ software. That like
but you have to be above, or just direct the software, because the software always says a number, and you have to make the meaning of that. So it's not much sense that your result is higher than the resolution of the microscope. That could be a typical example. It also happens with the accuracy of the ICP when you provide too many numbers. But there are common errors that everyone can do, and you are not going to repeat. Okay? Then I would like to also emphasize the accuracy of the description of the methodology used for the synthesis and also for the characterization. This is a very good thing that most of the students in the future can take profit of, because they are very well described. But that's a question. The first question, real question, is you use some modified methods, like Hammer's modified method and those things. Why?
Because in terms of cost, as example, for the time, we would like to test it if we can prepare the nanomaterial or the nanocomposite at low temperature with a low dose. So we would like to test it using the modified methods. And for the core shell, it's our method. It's because it's a novel adsorbent. It's not existing in the literature.
So these methods are not being optimized, I think. They have been just tested.
Yeah.
They have not any research in the methodology in terms of why this temperature or the other one is better to provide a good result.
Yeah.
Okay. This is one of the future works that might be done. Is in the optimization of such methodologies. Also, a different I will have a different approach from you in the classification of the analytic methods, because first you have talked about the
biosystem analyzer.
Bioanalysis, that is a colorimetric method.
Yep.
So in fact, it's not a different technique. And also you include the ICP as a characterization method when in fact it's an analytical technique, which determines the amount of metal after the digestion of the sample.
Okay.
But there are also some little differences in the approach. Now the question is, have you performed all the analysis yourself?
We did all the analysis using the ionic chromatography and gas chromatography with the 3 detectors here and with the turbidimeter. But only what we didn't analyze, we use the ICP from the Survey Analysis Chimica to determine the nickel. But for cadmium, we use the equipment of the department here of the UV vis.
Okay, that's the following question. Why? If you have an ICP that can measure most of metals, you use nickel, you use it for nickel and then not for cadmium. It's a problem of money.
Yeah, for the cost, if we have the equipment and we can overcome for this, not like paying money outside, and we have an equipment, so it's much better if we can do the analysis with ourselves.
Okay, so but the limit of detection should be better for the ICP, I guess.
Yeah.
Okay.
If I have here the ICP, I would like to do all of the analysis here with myself.
Yeah, well, I was fortunate because on my PhD research, I had an ICP for being used every day, so it was nice, but it was expensive for the group. So next, as Professor Ponsa said, the work is broad. I would say it's excessive. Okay, that's not a bad word. There are many, many, many things, and we only have to take them, or some of them are not very well taken. I say that some of the screening, it's an screening, of course, that something is missing everywhere, almost everywhere. You use some techniques for one sorbate and for one adsorbate, and then for a sorbent and the other, and it's a kind of puzzle that some pieces are okay, some are not complete. Okay, I understand that this first is a screening, and then you have the isotherms for the more important things.
Yeah.
I also suggest for other students that if you have the objectives of your thesis at the very beginning and you have them clear, then you can just say, well, this is this is good to be finished, or with this amount of information is enough. So I will say, now first question related to this is, what you have pursued, what would you have continued if you had the money and the time?
First, to optimize the core shell nanomaterial synthesis and to apply for the scale-up as a fixed big column before the scale-up system. This I would like first of all. But first, by optimizing and functionalize this adsorbent, especially for several contaminants, not only for anions, for heavy metals, for pesticides, as example. If we can use it also for gases, it will be much better. This is the idea from the beginning. If we have like one nanomaterial that we can eliminate several contaminants in one step, it's much better than using another different adsorbents. That's much better.
But your approach is just to test many things with one single adsorbent, rather than prepare new adsorbents with improved knowledge. Maybe that's okay.
No,
so you prefer to have one and try many other different things, or just think about a particular contaminant or group of contaminants and then design an adsorbent which is the perfect one or the optimal one?
No, our target in this case, if we can have one nanomaterial to apply to eliminate several contaminants, it's much better if we apply one adsorbent for one contaminant, as from the literature.
Okay, but things happen that specialized adsorbents usually get better results than general adsorbents. Yes. So that's a quite hard research to be done. Okay, and also regarding the future work that you have presented here, I think that, and also the optimization you said, that's more like development than research. Mm-hmm. So I think you want to improve the quality of the results instead of developing new knowledge of different fields which are not new from now.
Hopefully it will be the next step.
Sorry?
Hopefully it will be the next step.
Okay, so you are planning on a postdoc, I guess. Good luck. So, well, I would like to also emphasize that the classical approach you've done in most of the thesis has a turning coup de force when you talk about the microalgae. Then it's really interesting that you use a sorbing material, a sorbent, to be sorbed, like an adsorbate, into algae. So this is a kind of flipped research, I mean, flipped concept, and I would like to know which is or what is at the beginning of this story.
The beginning of this story is the separation of microalgae from water, because the methods such as sedimentation or flocculation only like around 50 to 60%. And if we can have like a material that we increase this harvesting efficiency in low time as a separation time, and if we can use this material for several times, it will be much better.
Yeah, but the concept of a solvent to be sorbed is like a very nice thing to emphasize here. Yep. I said that the research is broad and sometimes incomplete, and one of the things that you have done, like the isotherms, I'm not very happy with them, just to say. So you use many isotherms to describe the sorption of some of the compounds and some of the materials, but the fitting is not well or good for all of them. So most of them fits to Langmuir and are not fitting to Freundlich. And I don't know if they are fitting very well to Dubenin Rodskevich. Well, they're less than 0.9 in the results. So why you use some, and you report, I would say, the isotherms when the fitting is not good, because you cannot withdraw conclusions?
We apply the isotherm which is most applied from the literature, which is an example of Langmuir Freundlich. And we have like this information about a value for the maximum absorption capacity. And for another study, as we applied different isotherm for the 2 parameters, 3 parameters, and to test what will be the combination between the two. And what we found from this case, as I mentioned, for the methane, using the combination high R square. So just we apply the isotherm models from the literature. And we test in this case if we have high absorption capacity with high correlation coefficient.
Yeah, in fact, some of them are doubt. I would say it's not clear if it's Langmuir, Freundlich, or whatever. And you can use different approaches to say, okay, it's a kind of mixture behavior. Mm-hmm. But in other cases, it's clear that's a plateau. Mm-hmm. And if there's a plateau, it cannot be Freundlich. So I would have preferred that you said it's not fit into Freundlich, mm-hmm. instead of giving the values, which can be kind of confusing when reading the manuscript. Okay. Then I was surprised when reading the document about the amount of work, of course, but also because your sorbents are capable to sorb positive and negative species. That's quite strange. I mean, some of your materials are very, very good for fluoride and for phosphate. It's true that some improvement should be done, but I read some 100% recovery, mm-hmm. and also a kind of between 20 or 40% of recovery of cadmium.
Yep.
Can you explain that?
Yeah, because as I explained, for different possible adsorption mechanisms, sometimes it's like a strong interaction as a chemical between positively charged and negatively charged. And sometimes as ion exchange or van der Waals adsorption mechanism that could be for the cadmium with the adsorbent. So it's like a different adsorption mechanism for any contaminant with the adsorbent.
Could it be possible that some of your cadmium was kind of cadmium complexes, chloride complexes, which are negatively charged?
But cadmium chloride is soluble.
Yeah, but can be if the amount of chloride in the medium is very high. I don't know. I don't remember particularly all this composition. But if the electrolyte is containing chloride or whatever, maybe it's some negatively species which are.
Yeah, but we have in this case, our case, it's like milky water, which is a deionized water, and only we have the analyte.
So
the pollutants.
Then, what do you think it could happen if you use real water?
This is another study that I mentioned, the future work, the effect of the coexisting ions.
That you have many future work.
Yeah.
you have enough life to do everything? Okay, then another question or comment is like you said in the presentation that the tendency of nanotechnology development is exponential. So following the trend you plotted, it's more linear now.
More linear, yeah.
Yeah, it was a time some years ago that their growth was exponential. Now I think that it's not, and maybe we have to change the topic. Now it's not so hot. Now it would be more than bio nano or something like that would be really the hot topic. Finally, I will talk about the end of your document. Well, not. I have another question. Well, I was very, very glad when I read about the polyurethane, because I think I was the first working with that. I think the samples are provided to Amanda, so they were my own polyurethane that you tested, and I was really, really glad to see that someone else can do incredibly, impressive results with that. Do you think it's a material with some possibilities in the future?
Yeah.
Should I continue studying that?
Should be. Yeah.
Do you think any of the students would be interested to using mass-stress polyurethane?
Yeah, sure.
So the best, I would say that the first test we did with a mass-stress, a colchon, a polyurethane of something that was in the street, and we tested first, and then we bought the pure polyurethane from the supplier. So I was very, very glad of that and of the use of this intermatic synthesis. And now I go to the end. Now it's almost finished. The conclusions. I will say that the conclusions you reported here in the general conclusion of the manuscript, I don't like them very much. Not because of the content, but of the organization. They are results descriptive of your research, but I will prefer some philosophical conclusion of such amount of work, because you have many data, that's true. Some of the conclusions you reported here were more general and not so data-minded, but which is the most important conclusion of your thesis? I asked that to you.
Yeah.
Which one is it?
Because we did like a conclusion for each part, and we wouldn't like to do like again to repeat all of this conclusion again. So we mention of the major conclusion at the end, which could be in the general conclusion.
And for you, can you express it? One single conclusion?
Excuse me?
The more important, the best, the one that students will follow in the future?
I think so. If someone read it and it's interests this result, he or she will be back for the main parts of this work and read all of this in general.
Okay, so it's about 300 pages, so be careful. Now, the last thing, after this presentation and this act, I'll have the same idea like at the beginning, so that when you have a PhD thesis work, the result is not the thesis, it's the doctor, and you are very, very close to it.
only one more.
Thank you.
Okay. Well, first of all, I'm very happy because in the last year I couldn't read basically no scientific material. I must read a lot of things, and was very happy to use part of my summer in order to read this very hard book because it was wow. But I go to with that is first of all, congratulations to you, to your advisor, to your group. This work is a huge effort to develop, apply different techniques and methodologies, materials, too many things. This is really, I was thinking, what is the reason? Because this is not a normal thesis. What you think in a thesis is what Dr. Magana say. Normally you concentrate in a point and you go through this in trying to go depth. But this is the first thesis in this group in this area. And this is perfect because it's a lot of work. They tried, it was not so dead as we expect in any of the points in some of them, but you touch too many things. And it's very complicated to be expert in applying, in developing, to make the precipitation, the functionalization of the materials, everything. You touch, I was 5 different nanomaterials with 3 different technologies, all the characterization of previously to be used or after be used, application in gas phase, in liquid phase, catalytic application, absorption, anions, metals, solids, everything. Then it's impossible to be perfect. But on the other hand, you see the publication and you have 5 very good publications, plus 1, 2, or 3, because I expect in few hours you will have another more. This is several publications. This is good because this means that, like, it's normal in your group. You're doing a lot of work and scientifically right in the right way. This is, I must say again, congratulations. I have questions. It's always less than I was expecting because I prepared 15 and I think a lot of the question was this, but I will be back. Okay. Thank you again and congratulations. And go to the chapter 4. This is, for me, it's important. Every time I read about application of nanoparticles, I care about reproducibility. Because for example, you give data when you apply a methodology to prepare nanoparticles. You give me the size and the dispersion, but how many times you repeat the procedure? And what is the dispersion between the several batches?
For the nanomaterial or the elimination?
My problem is, if I want, it's a problem that I have. I always am thinking how to apply this, no? And this was the first question. The second will be about scale up, and the third about the price. Because this is, in order to be applied, I need to have very high reproducibility. And other people that I talk about nanoparticle, everyone tell me that it's very difficult to get have reproducibility between batches. Then if you prepare 10 grams of nanoparticle, and you prepare 2 weeks later or 1 month later 10 grams more, if you make the characterization of both batches, you have different characteristics or no?
Yeah, we did like this reproducibility, especially for the elimination of contaminants. We prepared already different batches of the nanomaterial, and after application for the elimination for fluoride or nitrate or phosphate, as example, we obtain more or less the same removal percentage. So this our nanomaterial highly reproducible.
Okay, then this is not, but you don't worry for the application. Okay, and about the scale up, it's possible to obtain not grams, kilograms or tons of this material, because when Sergio asked you about what will be the size of, and in some of the applications that you are trying to do, if you want to apply in the real world, you will need a very big reactor with a large number.
Yeah, to scale up the sense, it's not so easy to do it. and especially for the different properties of the nanomaterial. So we should be careful for this, and to overcome, as example, for this aggregation, if we can immobilize these nanomaterials into supports, as example, polyurethane foam. So in this case, we can reduce the aggregation of the nanomaterial. So I think will be easily to apply as a scale-up later, but after to produce nanocomposite.
About the price or about the cost, because if you use several kind of different nanoparticles, and some of them I see these are really not too much expensive because of iron, but the cerium and another is very expensive or no? I'm not in the area, then I don't know.
Rare earth metals in general, such as the cerium, it's expensive. So in our study as the core shell nanomaterial, we try to use low amount of cerium in terms of the cost. And later in the future work, we're gonna optimize these senses in terms of the release of cerium and another optimization for the elimination for fluoride, phosphate, heavy metals, and other contaminants.
Okay. I think Sergio asked you, but I'm not clear. Why you, when you in the chapter 4, you are making a screening, I have clear the different possibilities, and why you choose fluoride, phosphate, and nitrate?
From chapter 4, we did a screening not only for fluoride, nitrate.
Yeah, but why you try fluoride and not sulfate or another compound?
Because fluoride, as example, nowadays, overall the world, high concentration and so many diseases from this highly concentration, and even for the eutrophication due to the existing excessive concentration of phosphate and nitrates. So we focus about these contaminants, which is now a big serious problem overall the world.
Okay, this is your answer. When you are talking about organic compounds, you compare the activated carbon. What are the advantages of the nanoparticles against the activated carbon?
In terms of the separation, as example, using the magnetite, which has a high magnetic properties, so we can easily separate it due to the magnetic properties.
Okay, then if you separate it, you recover, why you make the analysis of the toxicity? Because if you are not going to discharge in the water, you are going to return, you don't care for the, I don't see why you care about the toxicity of these compounds.
Because if we have like any release of any adsorbent in the treated water, as example, or in the environment, it's very important to know if this release have a toxicity effect of the medium or no. Because it's not good if we eliminate any contaminant and at the same time we putting another. So it's much better to know all of this information.
But you check it in the concentration that you use in that absorption.
Yeah.
But if you release something, you will be very low. It's okay. It's only, but because I will try to see what are the toxicity of the very low concentration of my nanoparticles.
Yeah, that's why we already started to do this with a different concentration of nanomaterial, but the time is not enough to finish all of the study.
I think you answered because it was why in the chapter 5 you use a different concentration than the chapter 4, because when you're talking about water you use only one concentration that is very different to the other one. But I saw in the table that was more related with the published papers that you use the same concentration of the papers.
Yeah. And
why you don't use? You have a lot of material. Why you don't use your own materials in order to compare this with the others in the same?
Regarding the time.
Okay. In chapter 6, when you are making the absorption of fluoride is 60 minutes. 60 minutes to the absorption time. Will you put into the nanoparticles with the water in order to make the absorption? You need 60 minutes?
No, we did our study by using the 100 milligram per liter and 10 milligram per liter, and we found until 5 minutes for 10 milligram, we achieved the absorption equilibrium, and maximum 15 for the 100. Okay. So it's lower time to achieve the absorption.
There's a comparison with 60 minutes. There was a fight about that. This is the question.
We fixed the 60-minute because we are thinking if we have high concentration of fluoride to be sure to achieve the absorption equilibrium. But our study until 100, we achieve 15 minutes.
Okay, no, because if you are thinking about drinking water and you have a large amount of water, with 60 minutes will be impossible.
Yeah.
I think it's better, for high concentration of fluoride will be better. I think if you are talking about absorption methodologies in nanoparticle, sometimes it's better to make a mix between, because your system maybe work better in a low concentration or in a high concentration and combined with another that is less effective and can be cheaper. That is more related with the Sergio explained earlier.
Yeah, that's true.
Okay, when you are talking about absorption of phosphate and in order to recover in the chapter 7, you achieve a very high concentration absorption, more than 4 milligrams per gram, but this is high if you compare with absorption with another absorption material. It's a very low if you want to be applied for a real application. Do you think this? What kind of application are you thinking for this material? If you want to recover, I go to make the question again. If this material is very good for in compared with another one. There is one that is better, but it's more expensive. You say more complicated. But with 4 milligrams per gram, if you want to absorb or to remove a large, high concentration or a high amount of phosphate or recovery, will be impossible to do it with this material. Or I don't understand that.
Yeah, but for this we tried to have like an information by using at the cationic exchange polymer. If have like by using this support, we have a good or high removal efficiency or no. But at least when we observe something like that with a low removal efficiency, so we are thinking to try like a different supports as an anion exchange polymer, not cation exchange polymer, which will in this case we can obtain high absorption capacity in terms of the cationic one.
But you want to apply always for a very low concentration of phosphate?
No. Our target to apply our nanomaterial for high concentration to achieve lower maximum concentration.
What is the high concentration for you?
Based on the literature. If, as example, the industrial wastewater 430, so it's like higher than this limit to have an information if our nanomaterial can decrease this amount or no.
You make in three different chapters. You work with collaboration with another group. For me it's clear 2 of them, but I don't know exactly what the people of Manresa do in the chapter number 7. What was the
modeling? They did the modeling.
The modeling, but you make the modeling in another chapter, and you have the technology, and you have very good modeling in your group.
Because for the phosphates, this is the first part that we did here, this study, and I didn't have any more information how to do the I-third. So this is the first time for me to learn how I can do it. So this is the first step, and then I apply for the another part.
Okay. Okay, about the algae.
Yep.
It's nice. I think it's a different approach. It's perfect, but you are. Sometimes I think in the time that you need in order to use the algae, normally you recover and you make the settler in order to recover part of the algae and return to the reactor. With this system, there is any effects in the algae, and they dead or they are alive, or what are the if you made absorption after the deabsorption, what are the situation for this algae? You can use it or?
We didn't like this. This will be like the first study that with other colleague will be do like something like that, and another further optimization for the algae separation.
No, because in any case it's clear, because normally either if you have a settler in the outlet of the reactor, you have also algae that is good in order to remove it, and I think it's very efficient and nice. Okay, I go in, two more questions. About the catalytic reactor. It's nice because I tell you in the initial point that you touch too many things is important, and I see the collaboration with another. But you check the catalytic oxidation of the carbon monoxide. But did you check the effect of the CO2 in the reactor? Because normally the monoxide carbonide, there is not only the CO2, and then we are talking about catalytic points, or the CO2 and the CO. Sometimes they put in the same places, and I don't know if the efficiency will be lower if you have, for example, 2% or 1% of CO2 in your. I know that you cannot do everything. It's only a question if someone do it.
Yeah, this could be like for future work, if we have a mixture of gases, as example for carbon monoxide, carbon dioxide, and methane, to know about the efficiency of this material in presence of other gases.
Okay.
Yeah.
I don't do the last one. Okay. Officially, I must ask to all the doctors that are in the room if some of you want to make any question or any question to the candidate, because he is not PhD, and he will. No? No questions? Last option. He's ready. He answered very well to any question. Okay, then if not, we are going to suspender la sessió i deixeu uns moments perquè puguem fer els papers i decidir la qualificació.